I think I'm pretty smart, but there's always room for more knowledge. Let's go learn something. Welcome back, everybody. This is John with the Tech YouTube channel. I know I'm playing catch up right now. I'm at least a day behind, possibly two, and you're probably going to be getting at least two more videos today. Possibly, if I can get through it. If not, you'll probably get two tomorrow. Either way, I'm catching up. Hopefully you guys are doing pretty well. Today is actually pretty gloomy. Car got some new tires, so that's pretty good. Other than that, it's just been a pretty chill day. Getting some Christmas shopping done, and yeah. Oh, got a new light here. I don't know if you guys can tell that if the lighting is actually a lot better. I think I'm getting a little bit better with not really camera placement, because I mean all I have is really my webcam, and I also sometimes use my iPhone for my camera. But you know, as long as this channel continues, or as long as this channel gets better, who knows, I'll be investing a little bit more into the channel and hopefully make better content that's going to be more useful for you, And with that said, don't forget to hit that like button. Lets YouTube know to let others know about this video. And also don't forget to subscribe. Once you subscribe, hit that notification bell icon as well. It'll let you know when I upload some new content for you. But let's go ahead and go with Advent of Cyber 2022. And today's topic is going to be smart contracts. See what I did there? You can always get smarter. You can always learn something new. Now, some of you may know what smart contracts are or have heard about them, especially if you're into cryptocurrency, such as Ethereum, Bitcoin, Dogecoin. Dogecoin is still a thing, right? Me personally, I've actually delved into cryptocurrency before. I used to mine from home until I became someone that would just purchase cryptocurrency instead of mining. So I've done some of that stuff, and I still do, just not as much as before. But yeah, let's get on with the topic. So I've already downloaded the task files for this video, and yeah, let's read what we are going to be doing. After it was discovered that Best Festival Company was now on the blockchain and attempting to mint their cryptocurrency, they were quickly compromised. Best Festival Company lost all of its currency in the exchange because of the attack. Now, it is up to you as a red team operator to discover how the attacker exploited the contract and attempt to recreate the attack against the same target contract. Now, our learning objectives today are going to be explaining what smart contracts are and how they relate to the blockchain and why they are important. We got to understand how contracts are related, what they are built upon, and standard core functions. And we're also going to understand and explore a common smart contract vulnerability, which is probably what happened. So what is the blockchain? The blockchain is one of the most recently innovated and discussed technologies in the blockchain and its impact on modern computing. While historically it has been used as a financial technology, it's recently expanded into many other industries and applications. Informally, a blockchain acts as a database to store information in a specified format and is shared among members of a network with no one entity in control. By definition, a blockchain is a digital database or ledger distributed among nodes of a peer-to-peer network. The blockchain is distributed among peers or members with no central servers, hence decentralized. Due to its decentralized nature, each peer is expected to maintain the integrity of the blockchain. If one member of the network attempted to modify a blockchain maliciously, other members would compare it to their blockchain for integrity and determine if the whole network should express that change, which is what makes cryptocurrency and the whole blockchain technology pretty cool. If one database is hacked, all is not lost. It's got other ledgers, other peers or members that run their own servers to actually double check to make sure that that is actually what it's supposed to be. The core blockchain technology aims to be decentralized and maintain integrity. Cryptography is employed to negotiate transactions and provide utility to the blockchain. But what does this mean for security? That's a good question. If we ignore the core blockchain technology itself, which relies on cryptography, and instead focus on how data is transferred and negotiated, we may find the answer concerning. Throughout this task, we will continue to investigate the security of how information is communicated throughout the blockchain and observe real-world examples of practical applications of blockchain. And on each blockchain, there are smart contracts. Now, what's a smart contract? Smart contract basically is a program. You can program it. These smart contracts can be programmed in Rust or JavaScript, or even using new languages such as Solidity, Viper, and Yule, which have been developed to facilitate the creation of contracts. So if you have experience in programming in JavaScript or Python or Java or any other programming language, you'll probably understand a little bit more of what a smart contract is. But let's go ahead and go over what the functionality of a smart contract is. So building a smart contract may seem intimidating, but it greatly contrasts with core object-oriented programming concepts. Before diving deeper into a contract's functionality, let's imagine a contract was a class. Depending on the fields or information stored in a class, you may want individual fields to be private, preventing access or modification unless conditions are met. A smart contract's fields or information should be private and only accessed or modified from functions defined in the contract. A contract commonly has several functions that act similarly to accessors and mutators, such as checking balance, depositing, and withdrawing currency. So this smart contract will actually have other fields that are private but can be used in the smart contract itself. No one should be able to access the smart contract and a particular field, especially like checking balance, or in this case for cryptocurrency, you don't want to have someone go into a smart contract or into the blockchain and actually change how much cryptocurrency one account actually has. You don't want that. Ideally, what you would want is a function within that smart contract that someone else could call, and that function that's programmed in the smart contract will do all of that work for you. So that way, the only way that you would be able to access that function, say, a withdraw function or a depositing function, to update that total balance. All right, let's go ahead and continue. Once a contract is deployed on a blockchain, another contract can use its functions to call or execute the functions we just defined above. If we controlled contract A and contract B wanted to first deposit 1 Ethereum, Ethereum is a cryptocurrency, and then withdraw 1 Ethereum from contract A, contract B calls the deposit function of contract A. Contract A authorizes the deposit after checking if any predetermined conditions need to be met. So then, as you can see here in the diagram, contract B wants to deposit some Ethereum into contract A. So contract A has a function called deposit. Contract B calls on that function in contract A to say, I want to deposit 1 Ethereum, and then that function will run. It'll take the 1 Ethereum from contract B and add it to that account. All right, so now contract B wants to also withdraw 1 Ethereum from contract A. So it deposited 1 Ethereum, now it wants to withdraw the 1 Ethereum. So contract B calls the withdrawal function of contract A. Contract A authorizes the deposit if the predetermined conditions for withdrawal are met. So now contract B over here is telling, hey, contract A, I'd like to take 1 Ethereum out. Okay, no, so then that'll be it. Contract A authorizes the deposit if the predetermined conditions for withdrawal are met. Contract B can execute other functions after the ether is sent from contract A, but before the function resolves. So that can be a vulnerability. So it's almost like you can, as you can see here, contract B can execute other functions after the ether is sent from contract A, right? But before the function actually resolves. So contract A will just continue to keep sending them out, and contract B can keep calling that withdraw function. How do vulnerabilities in smart contracts occur? Most smart contract vulnerabilities arise due to logic issues or poor exception handling. Most vulnerabilities arise in functions when conditions are insecurely implemented through the previous mentioned issues. Let's take a step back to contract A in the previous section. The conditions of the withdraw function are balance is greater than 0, send Ethereum. So the balance is greater than 0 in contract A, because it's got to make sure that it actually has Ethereum in it to give, right? And if it does, we want to send it. At first glance, this may seem fine, but when is the amount to be sent subtracted from the balance? Referring back to the contract diagram, it is only ever deducted from the balance after the Ethereum is sent. Is this an issue? Yes. The function should finish before the contract can process any other functions. But if you recall, a contract can consecutively make new calls to a function while an old function is still executing. An attacker can continuously attempt to call the withdraw function before it can clear the balance. This means that the predefined conditions will always be met. A developer must modify the function's logic to remove the balance before another call can be made or require stricter requirements to be met. So what should be happening is no other functions, such as the withdraw function, until that withdraw function actually runs and subtracts it from the balance, no other functions should run. But that's not the case. The reentrancy attack. In the above section, we informally introduced a common vulnerability known as reentrancy. Reiterating what was covered above, reentrancy occurs when a malicious contract uses a fallback function to continue depleting a contract's total balance due to flawed logic after an initial withdraw function occurs. We have broken up the attack into diagrams similar to those previously seen to explain this better. Assuming that contract B is the attacking contract and contract A is a storage contract, contract B will execute a function to deposit, then withdraw at least 1 ether. This process is required to initiate the withdraw function's response. So in order for the withdraw function for contract A to actually work, you have to deposit something in first. So the attack function requires a value greater than or equal to 1. It's going to deposit 1 Ethereum, and it's going to withdraw all ether from account balance in contract A. So right now, contract A has a total balance of 200 Ethereum. Contract B balance has 1 Ethereum because it went ahead and deposited the 1 Ethereum. Now, what's going to happen now is contract B is going to access the withdraw function from contract A. And the withdraw function, some of the prerequisites for the withdraw function to run are required balance greater than 0. So we've got a total balance of contract A of 200. Contract B balance is 1 Ethereum, which is greater than 0. So we want to send the account balance to the contract that requested the withdrawal over here. Set the account balance to 0. Note the difference between account balance and total balance in the above diagram. The storage contract separates balances per account and keeps each account's total balance combined. We are specifically targeting the total balance we do not own to exploit the contract. At this point, contract B can either drop the response from the withdraw function or invoke a fallback function. A fallback function is a reserved function in Solidity that can appear once in a single contract. The function is executed when currency is sent with no other context or data, for example, what is happening in this example. The fallback function calls the withdraw function again, while the original call to the function was never fully resolved. Remember, the balance is never set back to 0, and the contract thinks of Ether as its total balance when sending it, not divided into each account. So it will continue to send currency beyond the account's balance until the total balance is 0. Because the withdraw function sends Ether with no context or data, the fallback function will be called again, and thus an infinite loop can now occur. Now that we have covered this, how this vulnerability occurs, and how we can exploit it, let's put it to the test. Sweet. Let's get this working. Alright, let's learn about Remix IDE. I have it running over here on the right side. Like I said, I've already downloaded the folder. I've also unzipped it, so we should be good. Both contracts are legitimate Solidity contracts. Getting familiar with the Remix environment. When you first open Remix, you want to draw your attention to the left side. There will be a file explorer. So over here, so we've got the, I believe this is going to be the file explorer. Yep. Search, Solidity compiler, and the deployment navigation. We will spend most of our time in the deploy and run transactions menu, as it allows us to select from an environment, account, and contract and interact with contracts we have compiled. Importing the necessary contracts. To get started with a task, you will need to import the task files provided to you. To do this, navigate to File Explorer, Default Workspace. Yep, I'm there. Load a local file into the current workspace. So let's go ahead and load the local file into the default workspace. So we'll go in here, we'll go into downloads, smart contracts. Alright, which ones do we want to put in there? You can select the necessary Sol files to be imported. We have provided you with both of those. Alright, let's take both of them and open. So we've got our Sol files in there. Importing the necessary contracts. To get started with the task. Okay, we've got that. Compiling the contracts. The next step is to compile the contracts. Navigate to the Solidity compiler and select that from the drop-down compiler menu. Alright. So we can go to Solidity compiler. And is that the one? A7. Well, it's 7. Is there an 810? Yeah, there is. Okay. We'll get that. Drop down compiler menu. Now you can compile the contract by pressing the compile button. But we want to compile contracts. Navigate to the and select that from the drop down compiler. Now you can compile the contract by pressing the compile button. You can ignore any warnings you may receive when compiling. Oh, okay. So you actually have to select the Sol files that you want to compile from up here on the right side of the compiler. So let's go ahead and compile the attack.sol. Let's compile that. Okay, and it says that we can ignore any warnings, so I will. Let's go ahead and compile ether.store as well. Alright, there's that. Deploying and interacting with contracts. Now that we have the contracts compiled, they are ready to be deployed from the deployment tab. To the right is a screenshot of the deployment tab and labels that we will use for reference menu element used to reference menu elements as we move throughout the deployment process. First, we must select a contract for deployment, and from the contract drop down, label 6, which is that, we should deploy the either store contract or target contract to begin. Alright, let's go ahead and go into the deploy and run transactions. First, we must select a contract for deployment from the contract dropdown, which is label number 6. So contract right here. So that's Ether Store. We should deploy the Ether Store contract or target contract to begin. For deployment, you only need to press the deploy button. So number 7. So right here. Alright, so let's go ahead and deploy it. Alright, well, let's go ahead and read on. We can now interact with the contract underneath the deployed contracts. Right there. A section to test the contract. We can deposit Ether into the contract to be added to the total balance. To deposit, insert a value in the values text box. And select the currency denomination of the drop down under label 5. And we will use Ether. Once setup is complete, you can deposit by pressing the deposit button. So how much should we deposit? Let's say we will deposit 1 Ethereum. And then we'll hit deposit. Ah, look at that. There's the deposit. So etherstore.deposit. That's 1 Ethereum. Cool. Note, when pressing the deposit button, this is a public function we are calling, just as if it were another contract calling the function externally. We've now successfully deployed our first contract and used it. You should see the balance update. Label number 9. It's just right there. 1 Ethereum. Right there. Now that we have deployed our first contract, switch to a different account. Drop down label 2 and select a new account. Alright, let's choose... Well, we'll choose the one down below. Right underneath it. And repeat the same process. This time you will be exploiting the original contract and should see the exploit actively occur. We have provided a summary of the steps to deploy and interact with the contract below. Select the contract you want to deploy. Yep, did that. Deploy the contract. Alright. So that contract is now deployed. Note, you need to provide a reference to the contract you are targeting before deploying the attack contract. To accomplish this, copy the address for EtherStore from label 11. You read through the discovery and explanation of the re-entrancy vulnerability. Recall that it must first deposit. Oh, okay. First, I need to deposit 1 Ether. And we're attacking. Oh, look at that. Balance is now at 13. And here's our flag. Okay. That was tough. Alright, let's see if we can go ahead and answer some of these questions. If not already completed, download the zip folder. It's already done. What flag is found after attacking? Is this one. Copy that and paste it. Let's submit it. There you go. It is correct. Are you up for a little challenge to celebrate day 8? Try your hand at these easy challenge rooms, Quotient and Agent T. I may go ahead and take a look at those as soon as I am done here. As you can see down below, day 9, we're going to be talking about pivoting. So there's a sneak peek to the next video that you will be seeing probably sometime soon. But man, my thoughts on this one, it was a head scratcher. I think some of the documentation could use a little more clarification, but I mean, hey, I struggled anyway. I don't know if you've done these already, and if you guys struggled through it as much as I did. But the important thing is, we finished it. We got the correct flag, and now this is probably just going to be something that I'm going to have to take a look at more and see exactly what's going on. I might have to go ahead and do this from scratch again, but that's the fun part of doing it this way, because all you got to do is just close this down and you can start all over again, straight from square one, and just practice that way. So anyways, if you guys like this video, again, please hit that like button. Lets YouTube know that this is good content to share out to other people. Also, hit that subscribe button and the notification bell icon so you know when I upload some new content. Until next time, you guys, which might be in a few minutes, I'll see you later. Peace. Have a good evening.